Section 6. Criteria and Additional Considerations for Cathodic Protection, CP. 6.1 Introduction. This section outlines the criteria for CP, which help assess whether a metallic pipeline system has been adequately protected against corrosion. Refer to Section 1, paragraphs 1.2 and 1.4. The level of cathodic polarization required to achieve effective CP may vary depending on environmental conditions. Consequently, a single criterion for evaluating CP effectiveness may not be sufficient for all scenarios or locations along the structure. It is the user's responsibility to choose an appropriate approach, potentially combining methods or criteria to ensure proper corrosion control, based on their expertise and the specific circumstances affecting the piping system. When assessing whether corrosion control has been adequately achieved, the conditions and factors listed in paragraph 6.1.2, special conditions, 6.2.1.5, and relevant considerations, 6.3, should always be taken into account, regardless of the chosen methods or criteria. Appendix B, optional, includes a list of international and regional standards that discuss external corrosion control criteria. 6.1.2 User responsibilities in selecting CP methods or criteria. The user must, 6.1.2.1, determine the necessary level of corrosion control to address specific conditions. A commonly used industry benchmark for effective external corrosion control is a reduction in the general corrosion rate to 0.025 mm per year, 1 mil per year, or lower. 6.1.2.2. Ensure that there is a method to evaluate the effectiveness of the chosen approach, whether used individually or in combination. 6.1.2.3. Document the effectiveness of CP or other corrosion control measures. See Section 11. In the absence of such documentation, at least one of the criteria in paragraph 6.2 should be met. 6.2 criteria, 6.2.1, steel and cast iron piping criteria, 6.2.1. One documented criteria based on empirical data that indicate effective corrosion control on specific piping systems may be applied to those or similar systems. 6.2.1.2. A minimum of 100 MV of cathodic polarization with either polarization formation or decay measured to satisfy this criterion. 6.2.1.3. A structure to electrolyte potential of 850 MV or more negative, measured using a saturated copper sulfate, CSE, reference electrode. This may be a direct measurement or a current applied potential with proper interpretation of voltage drops in the earth and metallic paths to assess polarization and corrosion control. 6.2.1.3.1. To evaluate the significance of structure-specific and environmental effects, the following methods may be applied. Measuring or calculating voltage drops, IR, in accordance with NACE standards. Using coupons to measure current density, corrosion potential, and polarization. Conducting indirect inspections, e.g., close interval potential surveys. Using probes or inspections to calculate corrosion rates. Direct examination of the pipeline to identify active corrosion. Other methods to verify sufficient polarization. 6.2.1.4. The current applied structure to electrolyte potential should meet or exceed the values set by the cathodic polarization or polarized potential criteria. 6.2.1.5. Special conditions for steel and cast iron piping. 6.2.1.5.1. If active microbiologically influenced corrosion, MIC, is suspected in anaerobic environments, higher polarization levels may be required. 6.2.1.5.2. Elevated temperatures, 40 degrees Celsius, might necessitate more negative polarization. 6.2.1.5.3. Mill-scaled steel may require greater polarization, 100 MeV. 6.2.1.5.4. In high resistivity, aerated, well-drained soils, less negative polarization may suffice. Note, ISO 15589-133 suggests less negative potentials based on soil resistivity. 6.2.1.5.5. Seasonal variations in soil resistivity must be considered when applying these criteria. 6.2.1.5. 6. AC power lines may influence pipelines, causing external AC corrosion. Increasing AC and DC current densities can exacerbate this. 6.2.1.5.7. In weak acidic environments, more negative polarization may be necessary to prevent corrosion. 6.2.1.5.8. Stress corrosion cracking, SCC. Risks should be addressed by managing environmental factors, coating types, and CP levels. The specific environments that cause high pH and near neutral pH SCC are discussed in detail. High pH SCC characteristics, typically found at the bottom of the pipe and associated with coal tar coatings. Achieving a polarized potential of 850 mV CSE helps avoid high pH SCC. Near neutral pH SCC characteristics, associated with minor external corrosion and stress factors, commonly found on polyethylene tape coatings, and the electrolyte is typically dilute carbonic acid, pH 6.8. 6.2.1.6 Overprotection. 6.2.1.6.1 Caustic overprotection. Excessive cathodic protection can create highly caustic environments, pH 13, degrading coating adhesion. Evaluate existing coatings for susceptibility to caustic disbondment. 6.2.1.6.2 Metallurgical overprotection. Excessive protection can generate hydrogen gas, causing damage to metals. Pipelines with non-homogeneous metallurgy may be more susceptible. 6.2.1.6.3 Increased polarization can lead to greater negative potentials and higher pH, which may negatively affect susceptible materials and coatings. 6.2.2 Aluminum piping criteria. 6.2.2.1 Criteria based on empirical evidence can be applied to specific aluminum piping systems or those with similar characteristics. 6.2.2.2 A minimum of 100 MeV of cathodic polarization, with either the formation or decay of polarization measured. 6.2.2.3 Precautionary notes. 6.2.2.3.1 Voltages should not exceed 1,200 MeV CSE unless prior tests show no significant corrosion in the given environment. 6.2.2.3 2 Aluminum can corrode in alkaline environments, so testing should be conducted to determine the effect of CP on the local electrolyte. 6.2.3 Copper piping criteria. 6.2.3.1 Documented criteria for corrosion control effectiveness may be applied to copper piping systems. 6.2.3.2 Minimum of 100 MeV of cathodic polarization, with either formation or decay measured. 6.2.4 Stainless steel piping criteria. 6.2.4.1 Documented criteria for corrosion control effectiveness may be applied to stainless steel piping systems. 6.2.4.2 Minimum of 100 MeV of cathodic polarization, with either formation or decay measured. 6.2.4.3 Precautionary notes. 6.2.4.3.1 Protective coatings should be applied to reduce CP requirements for stainless steel buried in soil or groundwater. 6.2.4.3.2 Be aware of changes in environmental conditions that may affect corrosion or polarization values. 6.2.4.3.3 Avoid polarized potentials in the cracking range for high pH SCC. 6.3 Relevant considerations. 6.3.1 Factors affecting CP criteria include the type of electrolyte, resistivity, pH, moisture, and aeration. The pipe's metallurgy, welds, and coatings should also be considered. 6.3.2 Operational factors like coating type, proximity to other pipelines, and temperature should be evaluated. 6.3.3 Measurements for CP criteria should be taken with reference electrodes at 25 degrees Celsius, 77 degrees Celsius. 6.3.4 Inline inspection, ILI, can help determine the presence or absence of corrosion damage and assess external corrosion control effectiveness. 6.3.5 Changes in electrolyte conditions, CP system, or structure configuration can affect polarization levels, and these factors should be considered. 6.3. 6. In mixed metal systems, the CP criterion for the most active metal should be used if accurate measurements for that metal cannot be taken. 6.3.7. When piping is connected to electrical grounding systems, the CP criterion for the piping should be applied. 6.3.8. Amphoteric materials like aluminum or lead may require electrical isolation if high alkalinity caused by CP could damage them. 6.4. Target potentials. 6.4.1. Once effective CP is established at a location, the corresponding minimum potentials can be used as target potentials for ongoing monitoring. Periodic reassessment is required. 6.5. Alternative reference electrodes. Further information on the use of alternative reference electrodes will be provided.